My name is Rebecca Steinberg, and I'm a second-year master's student working on the final steps for this project. Today I'm going to discuss with you the progression of work by our project team to develop a GIS prediction tool for post-mining water level in Ohio. We wanted to start out with a special thanks to all of our sponsors on this project. Some quick background for those not familiar with the project. This is an OSMRE funded grant project to address the need for a better prediction method for post-mining water levels in underground coal mines. This is a value that is required by SMACRA, and the current use of top of coal for an estimate has been deemed insufficient. A better prediction method would ultimately save companies the cost of reclamation in the long term. Specific to this project, our main goal has been to develop an empirical statistical predictive model of post-mining water levels to be implemented in ArcGIS Pro. Our main outputs are going to be the predicted points of post-mining water level, as well as areas at risk for surface discharge from these mine pools. Here we have a flowchart describing the progression of work on this project. I'll be using it to refer back to throughout the presentation. You have here at the top, beginning with our concept of using GIS to predict the post-mining water levels, and then from there going and actually receiving the grant from OSMRE, and then selecting graduate students to work on the project. Once graduate students were selected, the next big step in our project was actually receiving data that we had requested from ODNR and extracting from those 28 mine permits the majority of the data that was used in this project. This required going through thousands and thousands of PDF pages to ultimately extract almost 3,000 final data points that were used in our statistical analyses. Once data was extracted and manually entered into Excel to be easily worked with, graduate students Lindsay Schaefer and Fred Tomasi worked to develop methods for analysis. These initial methods didn't all work out the way we had hoped, so time was dedicated to defining what approaches worked with the available data set. Some of the initial approaches for analyzing our data set was to look at defining specific aquifers and water tables in the area, as well as averaging out the recorded potentiometric head measurements and only looking at data from the mine permits that was determined to be pre-mining data. We quickly realized that defining specific aquifers in this area wasn't possible. Most of the aquifers are discontinuous and there is a lack of reported water withdrawal data. We also discovered that averaging out the potentiometric head measurements limited our larger data set, and that pre-mining was not always pre-mining in the sense that we had defined it with the amount of mining going on in the surrounding area. So we were not able to distinguish data as pre-mining from our data set. So through the work of Fred and Lindsay, we were able to determine alternate approaches to analyzing the data that addressed the issues that we had discovered. To address the lack of water withdrawal data, we were able to use volume of coal extracted as a proxy for that void space. Coal extracted then was used as a definition of time, removing the issue of separating pre- and post-mining data. This allowed us to use all the complete data that had been extracted from the permits, thus using each well measurement instead of maximum, minimums, and averages. We also used the elevation of bottom of the coal layer to extrapolate the predicted water levels at the well locations down to the coal seam. The interconnected nature of the area hydrology has allowed for this. Thus, finally, this data set was reanalyzed with the statistical methods developed by Fred and Lindsay. The rerun analysis of this new data set is where my work comes in. This analysis was used to select our final prediction equation from our best results. So I'm going to quickly walk through our process for selecting this equation. So these are the methods that were used by Fred and Lindsay in the initial analysis, but also used on the rerun analysis of the new data set. We first used the program unscrambler X to run 4 different statistical analyses. First being MLR, which was originally deemed not appropriate because our variables in this project are not independent from each other. PCA was used mostly in the initial analysis to identify the actual variables, but was also used in the rerun analysis to determine consistency in variable relationships. PCR did produce a usable regression, but PLSR produced a usable regression with even less errors, so PLSR was the focus of the results from the unscrambler analysis. The second program that was used was NeuroShell 2, which is actually an artificial neural network program, and actually produced a complex regression that had even less error than PLSR. From the initial analysis, 11 variables were determined to be significant and were used consistently in the rerun analysis. We had 11 variables: the surface elevation of the well, bottom elevation, overburden thickness, thickness of mined coal seam, thickness of shale and clay in the overburden, as well as the thickness of sandstone and limestone in the overburden, and the final total coal thickness in the overburden. We also used accumulated coal volume, area of underground mines within a 4-mile buffer of the proposed underground mine, and the average annual precipitation of the area. Here we also have a map displaying the mines in Ohio that we looked at, the blue being the study mines, which were the 28 permits that we had requested from ODNR, 13 of which we actually were able to use in our tool development. And then the orange and purple are the other surrounding underground mines. So a quick look at the results from the PLSR analysis. Here we have a correlations loading chart, which shows the relationships of the variables to each other and to the predicted post-mining water level variable. The outer ellipse here shows 100% of explained variance of the data, and the inner ellipse shows 50% of the explained variance. So the closer the variable is plotted to the outer ellipse, the more of the data variance that variable explains. And the closer that variables are to each other, the more related they are. So you can see up in the upper right corner that the surface and bottom elevation are not only very close to the outer ellipse of 100% explained variance, but also very close to the predicted post-mining water level variable. While we didn't end up using the resulting equation from PLSR, I thought it was important to show the resulting regression from the initial analysis as well as the rerun analysis, which displays consistency in not only the variable relationships, but also the resulting regression itself. On the top you have the initial regression run, as well as on the bottom you have the rerun analysis with the larger data set. Both have decent R-squared values, as well as a slope close to 1. While PLSR provided a usable equation, the artificial neural network produced a slightly more accurate equation due to the higher complexity. We decided to use the resulting equation in the final tool building, but wanted to test various selection parameters in NeuroShell to develop the best results. This chart here shows the 3 different optimization methods tested with each of the 6 types of selection criterion. These results then were compared based on how many of the variables were retained, as well as still having a high R-squared value but a low complexity of the resulting algorithm. To select the final equation for use in the prediction tool, the NeuroShell results table was then sorted by the values we were comparing. Ultimately, test run K, highlighted here, was selected as it did retain all the variables we deemed significant through our previous analyses. It also has a high R-squared value of 0.9906, which was higher than 0.98 of the PLSR regression. And it also had a lower complexity or length than the other tests that had similar R-squared values. So this is what the resulting equation from test run K actually looks like. Before variables can be put into the algorithm, there is a transformation that needs to be done, as well as a transformation back from the predicted value to the actual water level predicted. So once the final equation was selected from the artificial neural network results, we were able to move into the tool building development stage. Here's a screenshot of the tool package once it's opened in ArcGIS Pro. For this webinar, though, I'll be focusing on the background development of this tool. Our second webinar will be the actual tutorial for using the tool. This is a screenshot of what the actual prediction tool looks like when opened up in the Geoprocessing tab in ArcGIS Pro. This is just an example to show the inputs that I'll be describing within the process of the development and why they're important. This workflow diagram is what was used as reference for actually constructing the tool within ArcGIS Pro. And I'll be referencing back to this diagram as I describe each process. On the left, you have the required inputs from the users, which is in that screenshot I just showed. You have the data tables as well as the surrounding shapefiles for underground mines, the shapefile for proposed mine extent, as well as the area DEM. In between, you have in the yellow diamonds the various ArcGIS tools that will be used in the process of extracting variables for the algorithm application. And once the algorithm is applied, then tools that are comparing those points of prediction value to the area DEM, so that you have on the far right the final output, which are points of risk of surface discharge. So I want to start out with the required inputs for the tool, which are on the left of the flow chart that we just looked at. First and most important being the data sheets that contain the well and borehole data from the permit of the proposed mine. This is the bulk of the data used in applying the algorithm itself. This data will need to be entered by the user into provided Excel sheet templates prior to being added to the map. Correctly following the format of these Excel templates is essential to the tool running smoothly. These are the values that are required for entry into the Excel templates. Both the wells and the borehole data sheets are containing mostly data from the permits, but some of the values will need to be collected from other sources or calculated from that data. But more details on how to enter this data into the Excel sheets will be provided in the second tutorial as well as the user's guide. The next required inputs are the shapefiles of the underground mines of the area, being both the pre and post SMACRA shapefiles downloaded from ODNR, as well as the extent of the proposed mine to be run through the analysis, a shapefile that may need to be created from documents within the proposed mine permit. More details on this as well within the user's guide. The final required input is the area DEM, or digital elevation model. This is included as a default within the project package for the state of Ohio, but can be changed to a DEM from the user. So now that we've gone over the required inputs seen here on the left, I'm going to go over the tools in between that run in the background of the tool to extract the final variables and actually apply the algorithm itself and determine the final outputs of the tool. So the first step of the tool is to actually combine the two data sheets that are entered by the users. This is using a tool for adding the Excel tables to points on the ArcGIS map, actually projecting those points. And then once those points are projected, the spatial join tool is able to combine these points and determine area lithology for the well locations. Next, the final variable needed for applying the algorithm is extracted by the tool through using the buffers and summarize within tools. It actually creates a 4-mile buffer and calculates the acreage of underground mining surrounding the proposed mine. That value is then added to the variable table of the well locations. Once all the variables required for running the prediction algorithm are extracted and put into the same table for the well locations, the application of the algorithm itself is done through a custom Python script. These variables are automatically pulled into the equation, and then the predicted elevation of post-mining water level is directly output back into that same table for these locations of the wells as prediction points. So the final step of the tool is to actually compare the points of predicted post-mining water level to the area DEM. This is done through first converting the raster to points and then spatially joining those points to our points of predicted post-mining water level to determine the closest elevation value to our predicted post-mining water level location, and then actually calculating the difference between the predicted post-mining water level elevation and the DEM value. So from there, then the final value in the variable table will show if the predicted post-mining water level elevation is above or below the area DEM. So those were the tools that actually run in the background of the prediction tool once the user has run it. And now I'm going to describe the outputs for the user that the tool produces. This is an example of what an output might look like once the user runs the tool, and the final points of predicted post-mining water level have the points of predicted head, but also the comparison with the DEM as the value distance to surface from the predicted head. Again, more details on how to look at the final results are included in the next tutorial as well as the user's guide. So the final direct outputs of the tool are point shape files of the Excel sheets that were input by the user, providing the user with points of wells and points of boreholes for continued use. There's also the point shape file of at the well location predicted post-mining water level. And finally, a third shapefile layer that is the points of predicted post-mining water level with the values of elevation above or below the DEM, indicating areas at possible risk for surface discharge. So this final output layer actually allows for some assessment of the potential effect of this proposed mine on the area and looking at the area hydrology and surrounding areas that might be affected if there was surface discharge to occur. There's also the possibility of interpolating those prediction points into an actual surface to get more of a widespread area of risk indication. So quickly looking back at our project flowchart, we've come to the final stages where we have put together our webinars and completed putting together the predictive tool package. Some of the challenges encountered throughout the work on this project have been mostly within the actual extraction of data, since we did have to manually extract data from PDF files into Excel sheets. That took us a lot longer than we initially expected it to. The other issue would be in actual consistency of reporting of well data. There's an inadequate distribution of the wells for a spatial analysis, but also perhaps a inadequate distribution in terms of actually characterizing the area hydrology. There is the possibility of looking into nested piezometers, which are used in Pennsylvania to actually monitor post-mining water levels. There's also continued work possibly in looking at spatially interpolating a prediction surface from those points of predicted post-mining water levels. And there's also the possibility of using borehole locations instead of just the well locations to add more points for possibly interpolating a surface. So our final project takeaway is that we were able to complete our main project goal, which was to create a user-friendly and publicly accessible empirical statistical model to predict possible discharge risks of post-mining water levels. The project package is available for download by the public on watershedData.com with the link provided here. Also hosted on that site is the second webinar, which is a tutorial for actually running and applying the tool itself, as well as the necessary templates for running the tool and the user's guide itself. Thank you for your interest in our work, and like I said, more info on this project can be found on watershedData.com. Thank you.